everyone. My name is Jenny Garcia, and I am a senior at California State University, Channel Islands. This summer, I focused my research on the effects of the Rio Salado and Rio Grande confluence on macroinvertebrates. As many of you know, the Rio Grande spans from southern Colorado to the Gulf of Mexico. Its main use is for agricultural irrigation. This river creates a riparian habitat for various species, such as both the endangered Rio Grande silvery minnow and the southwestern little flycatcher. This body of water is a loaded ecosystem. What does loaded mean? This means that it is a running, flowing body of water, as opposed to lentic, which would be a pond or lake. The high majority of the sediment composition of the Rio Grande is sandy. However, from the tributaries that feed into it, that creates some sort of diversity. One tributary that is of special interest to me is the Rio Salado. As you can see from this photo, the whitewashed area is the Rio Salado coming into the Rio Grande. As it joins the Rio Grande, it creates an area called a confluence. Confluences are considered biodiversity hotspots because a heterogeneous mixture of sediments occurs in this area, thus creating diverse niches for various species to exploit. Now, some of these organisms are macroinvertebrates, which live on the riverbed, and they spend most of their life, or part of it, in the water. This makes them really good bioindicators of an ecosystem because their survival is highly tied to water quality, and thus with the higher pollutants, there is lower diversity. And last but not least, these little guys are also food for larger invertebrates and rodents. So the underlying theme of my project this summer was based on sediment disturbance. And the reason why I focus on sediment disturbance was because it affects a lot of things, but I focus on two things: macroinvertebrates and periphyton. Periphyton is a mixture of cyanobacteria, microbes, and detritus that grows on rock surfaces. Now, why did I bring periphyton into the mix? Well, macroinvertebrates eat the periphyton, and periphyton can be used as another measure of sediment disturbance. So based on all of this, I came up with the main question that I wanted to answer this summer. How does the confluence affect benthic macroinvertebrate communities? So how did I execute this? First, I designated 3 sampling sites along the confluence. The red designates the upper confluence, the green is confluence, and yellow is downstream. At each of these sites, I had 4 replicates, and I sampled for 3 things: sediment, macroinvertebrates, and periphyton. Before I collected sediment, I looked at flow velocity. I looked at flow velocity because I wanted to make sure that I collected sediment from areas of equal flow and thus disturbance. And here's a photo of myself downstream and one of my mates boarding upstream, with about 10 meters between us, and she would let go of an orange and I would catch at the end. Somebody else would time it, and that's how we figured out velocity the old school way. For my invertebrate sampling, I used a 1 centimeter core of a 60 milliliter syringe. I inserted it into the riverbed and took 4 cores from my 12 sample sites. I preserved the sample in ethanol, and later in the lab, I sifted through it, sorted, and identified it. All of my macroinvertebrates were identified to them. For the periphyton, I had a similar procedure. I used the same syringe, however, this was only inserted to 2 milliliters. I took 3 cores from the sites, wrapped them in aluminum as soon as possible to stop the photosynthetic process, and then later put the samples through a spectrophotometer to get results. For the sediment, I walked into the river to my sites with a bucket and shovel in hand. I scooped up the sediment, took it back to the lab, dried it under the hot New Mexican sun, sieved it to get proportions of the sediment sizes, and later spray painted it. Now, before I move on to the next slide, I want to say that the sediment disturbance experiment was going to be done at the confluence itself. However, the rains came and the water level was too high to go into, so I opted to artificially reproduce this, which is this. So this is a setup that my mentor and I quickly sketched out, and this is how I executed it. So this is out here in the patio, and yes, that is a cooler holding up my hose. So the top bin on the table has a matrix of sand, and inside of it I have my sediment sample, and I did this for all of my 12 samples. The bin that has a lid going into it, that bin collected the excess water, which dumped out into the sand and watered the plants, so it was great. On the right photo, you can see an aerial view of the sediment sample spray painted in the sand matrix. And for each, so how I had previously mentioned, I took velocity measurements. So here I recreated that, and I standardized the hose and I marked it where I deemed was low, medium, high velocity. So that's how I standardized it, and the samples ran for 30 minutes each at their respective velocity. So what did we come up with? When I looked at overall abundance, there was no significant difference. However, we do see a trend, and it appears that downstream had the most abundance. When I analyzed the taxa, we did have a significant difference. We have a p-value of 0.021, which means that this is correlated to the sites, that there is this would explain that the taxa diversity is tied to the different sites. So what kind of diversity did I have? I had a total of 8 families, and otherwise noted, if they're not otherwise noted, there's something else, but most of them are families. And they are arranged from increasing to decreasing abundance. So the most I had conmids, and I just had the one big A-fly. So the takeaway from this table is to show that the upper confluence didn't have as much taxa distribution, and I believe this because in the upper confluence, most of the composition is sandy, so each sand particle is very light and moves, and so it acts like sandpaper scraping off and very fine. So the organisms there don't have a stable food source, so you would only find the most tolerant taxa there. When I looked at biotic index, there was no significant difference, and what biotic index is each species is given, or family, is given a biotic score, and this biotic score is plenty of people working with using biotic index, but what this means is it is a range from 0 to 10, and the closer you are to 0 means that your organism is the most sensitive, and 10 means that's more tolerable. So we didn't really have overall any sensitive organisms that would give us any insight into the ecosystem health. So this is very exciting. These results are actually hot off the press. I got these yesterday. I don't have any stats on this, but however, it's very exciting to me because there appears to be a trend, and there is a lot more, it appears that there's more chlorophyll downstream. And this would make sense because downstream you have a lot of bigger, heavier stones and cobbles and rocks, so they don't move as much. Therefore, they don't disturb the peripine. Therefore, more diversity can live there. Now, for the sediment disturbance experiment, I didn't really see a trend here. I think mainly because there might have been some issues with how I set up the experiment. I had just sand, overall sand, as my matrix, so I probably need to have I had the same sediment that the sample would have seen naturally in the confluence. Also, maybe the way that the water was falling. I noticed even though I had the hose inverted to have a more homogeneous fall, I noticed that some holes were still being dug, so maybe that affected the flow as to why I didn't get the results that I would have liked to see. In the future, it would be interesting to collect the same samples and compare it to post-monsoon season as I collected everything in the pre-monsoon, because when the monsoon rains come, there is more water, higher discharge in the river, and this means that that could create higher disturbance, so that would be interesting to compare to what I did. Lastly, I would like to thank my mentor, Asha Burdett, for being awesome this summer, Emma Swan for being an awesome program coordinator and make sure everything went smoothly, and all of my fellow REUs that came out with me to dig up some sediments, and also to Becky Bixby, which she came in for me last minute and she helped me with a spectrophotometer to run my colorful samples. Thank you.